Let's begin the machine learning walkthrough inside Flex83. The prerequisite is data availability within FlexLake, an open table format built on Apache Iceberg. This serves as the enterprise data lakehouse, housing operational, transactional, and IoT datasets. From here, teams identify datasets relevant for machine learning use cases, such as customer analytics, transactions, or IoT sensor telemetry. Each dataset contains temporal, categorical, and operational attributes, including potential target variables for prediction. For example, anomaly detection in sensor data. Model creation begins in ML Studio, where FlexLake tables are directly accessible. The platform guides users through a step-by-step workflow, starting with source selection, followed by profiling, data cleaning, feature engineering, and model training. During profiling, Flex83 scans dataset structure and quality. It evaluates volume, schema, and completeness, including null values, duplicates, and distribution patterns, providing a statistical foundation before modeling begins. Column-level analysis surfaces quality gaps, such as missing values or skewed distributions. These insights drive cleansing strategies, ensuring reliable model performance. Smart recommendations accelerate preparation. Flex83 highlights transformation actions, such as encoding categorical fields or removing non-contributing attributes. For example, device IDs or timestamps that don't influence anomaly prediction. Users can apply filtering and transformation rules, including threshold filters, column drops, and identity removal, ensuring generalized model learning rather than device-specific bias. Null handling strategies such as mean imputation prepare datasets for feature engineering, while outliers can be clipped or normalized. A preview validates transformed data before committing changes. The clean dataset is versioned and stored for downstream modeling. Next comes feature engineering, where attributes are transformed for learning. Flex83 recommends optimal treatments, such as normalization or encoding. Previewing engineered data confirms transformation outputs. Categorical fields become encoded ready for algorithm consumption. Feature datasets are then materialized, with governed naming and lineage, ensuring reproducibility across experiments. With data ready, model selection begins. Target variables are defined and features finalized. For anomaly detection, classification models apply. Training configuration is auto-prepared, including train test splits, hyperparameters, and experiment tracking. Model training is then executed. Trained models are logged to the registry, connected to MLflow governance, ensuring lifecycle traceability. Model accuracy and performance metrics are instantly available, including precision and recall. Visualization tools explain model behavior, highlighting feature contribution and prediction influence. Confusion matrices, ROC curves. All trained models are centrally cataloged with governed version control. These models can now power predictions across streaming pipelines or batch datasets using simple prediction APIs, embedding AI directly into operations.